This is the first in a series of videos talking about the words we use to describe motion. In this video, we're going to focus on the words distance, displacement, speed, and velocity. In this unit, we are studying what is known as kinematics, where we look at motion without thinking about the forces that are involved in causing this motion. So we're just looking at things moving sort of by themselves, not why they move. We already use many different words to describe motion. We might say that something's going fast, or it's stopped, or it's speeding up, or slowing down, turning. Those are all motion description words, but they're very general. We've got some specific vocabulary that you need to master to be successful in physics, because this specific vocabulary is connecting to the underlying mathematical principles that really are what the foundation is for this particular science. Even though we're not going to be doing a lot of that math, we still need to use the correct vocabulary. In general, there are two main categories of words that describe motion, and you need to get these straight in your head. There are scalar words. Scalar words are words that are motion that is represented by a number, of course, including the units always. Numbers by themselves don't mean anything in science. And then there are vector quantities, and these have a number and a direction. So the direction is the key part when you're talking about a vector. Their direction could be directions like a compass, north, south, east, or west. Could be right or left, up or down, positive or negative. Those are all directional words that we will see associated with a number when we're describing a vector. So really quickly, let's run through some examples and ask yourself, is this a scalar? Is it just a number, or is it a vector? Is there some kind of direction involved in it? So 5 meters, of course, would be scalar. 30 meters per second east, there's a direction, that's a vector. 5 miles north would be a vector. Again, a direction is included. 20 degrees Celsius is just a scalar quantity. 256 bytes, a scalar. 4,000 calories, scalar. 4 centimeters down would be a vector. And 7,000 feet to the right, another vector. So see how the various directional words are added to the numbers to make a vector. Now I want to talk about the two words distance and displacement. Distance is a scalar word, and it refers to the total amount of space traveled through by the object in motion. Direction is not involved when you're talking about distance. So if we look at this little illustration down here, let's imagine you walk out behind school and you're going to walk a rectangle in the soccer field. And so we'll use the directions of the compass. So you're going to first walk north for 2 meters, and then you're going to turn and walk east for 4 meters, and then you'll walk south for 2 meters, and then west for 4 meters till you come back to your starting point. To calculate the distance, then, we add up all of the lengths of the sides of this rectangle, 2 plus 4 plus 2 plus 4, and it tells us that our distance traveled is 12 meters. But distance and displacement are not the same thing, because displacement is a vector quantity, and it refers to how much the object, in this case you walking around the soccer field, has moved from the original position. This includes thinking about what happens with directions. In this little example down below, you started over here on the star and you walked all the way around the soccer field and you came back to the same spot. So your direction, in a sense, canceled each other out. When you moved north and then you moved south on the other side of the rectangle, that northward movement was canceled out, and the same thing is true of the east and west movement. And so the displacement was actually 0 meters. Even though you spent some energy and time walking a 12-meter rectangle, the perimeter of a 12-meter rectangle, your displacement was 0. You didn't go anywhere. You came back to that original position. So I have an example problem. Actually, it realistically is not a terribly good example problem, because it has this cross-country skier sort of turning around very rapidly. And if you've ever done anything with skis on the bottom of your feet, you know it's difficult to turn very, very fast. But we have this, imaginary scenario where at the starting point at t equals 0 minutes, our skier here is at point A, and they get out in a bound of enthusiasm, and they ski over here to point B, traveling 40 meters plus 100 meters plus another 40 meters. So they're going 180 meters on this first pass. And they get to point B after 1 minute, and they turn around and ski back. But I think they were kind of tired at this point, because in the next minute they only make it to point C, because at t 2 minutes they're over here at point C. And so there they do another 40 meters plus 100 meters. So that would get us up to, 320 meters. And then very, very tired, this person turns around again and takes another minute to ski over to point D. So at the end of 3 minutes, they've added another 100 meters. So 320 was our last measurement. So total now we've gone 420 meters over these 3 minutes. If we wanted to calculate the speed, we could do so and divide that up. So that was the total distance, 420 meters, but basically it was just going back and forth. The skier started over here on point A and ends over here on point D. So the displacement is just going to be the distance from A to D. And that's only going to be the 40 plus 100. So the displacement would only be 140 meters. So even though the distance traveled was 420 meters, the amount that the skier moved from the original starting position at A was only 140 meters. So that gives you an example of the difference between distance and displacement. Two other words that we'll be using quite a bit in this unit are speed and velocity. So speed is a scalar quantity, so it uses a number without any direction involved. And of course, it's a measure of how fast something is moving, or we can think of it as the rate at which an object covers a certain amount of distance per time. You're familiar with speed values by driving a car, 60 miles per hour. So the 60 miles was the distance, the time involved would be 1 hour. In contrast, velocity is a vector, and velocity refers to the speed of an object, but in a given direction. So it's like a speed calculation plus a direction added. An object could be moving but have no velocity if it doesn't go anywhere. So you think like walking on a treadmill would be an example where you would have speed, your legs could be moving at a certain speed, but you will have no velocity. And objects only have the same velocity if they match both with the same speed and the same direction. So any change between two objects that are not moving at quite the same speed or not in the quite same direction, they have two different velocities. We often draw vectors as little arrows. So the arrow, can be used to show what direction the velocity is moving. Sometimes it's also used to show how strong it is. So a short little vector says, there's not a high velocity number, but a long arrow would tell you that this velocity is a bigger number. And then we point that arrow towards whatever direction the object is moving in if we're using these arrows to show velocity. So when we're talking about speed, sometimes we want to be talking about the instantaneous speed, which is the speed at a moment in time. So any one particular moment, right now, this is the speed that's happening. But really, more practically, most of the time when we're talking about speed, we're talking about average speed, which is the average of all the instantaneous speeds over a certain amount of time. When you're talking about, driving somewhere, you know that you are not staying at one particular speed the whole time. You've got to take some time to speed up. You might have to stop for a stop sign or a stoplight, or if you're on the interstate, you've got to, wait. Somebody's slow in front of you and you can't get around them, so you have to slow down for a little bit, and then you speed up to get around them. And so in reality, you are making many, many little changes in speed over the time that you're driving. And so you can figure out what that average speed is by divide that total distance traveled by the total time spent traveling. And we will use this average speed calculation on some problems, so you want to get familiar with it, where the distance traveled divided by the time of travel will give you your average speed. So you get an example like this, to get to your favorite vacation spot. Your family traveled a total distance of 440 miles. The trip took 8 hours. What was your average speed? So remember, your speed is the distance divided by the time. So our distance here was 440 miles, and our time was 8 hours. And we just do the math. We divide 440 by 8, and that tells us that the average speed was 55 miles per hour. So use these check for understanding questions to just check your own understanding right now, or you can use them to study for the test. There'll be many activities we're doing in class to help reinforce these ideas, but these are the important things you need to know from after you've completed this video. Just being able to define the difference between a scalar quantity and a vector quantity, distinguishing between distance and displacement when we talk about an object's motion. Do you know how you calculate then distance and displacement if you've been given a story about how something is moving? Can you explain the difference between speed and velocity and how they're related? Can you identify what needs to change to make velocity change? And can you calculate average speed? If you're not sure about any of these things right now after watching the video for the first time, go back through and make sure you get this information in your notes because, of course, you will need it when it comes to the quiz.